Okay, so in this topic, atomic structure, we're now going to start by looking at the development of the atomic model to the point where we're going to go from ancient history to where we are in the modern day. So, back at the very beginnings of the ideas on this, we have 5th century BC, Democritus. Now, Democritus came up with the idea that if you cut things down into smaller and smaller lumps, you'd eventually get to the point where you couldn't get any smaller, and he called those small indivisible lumps atomos. It took quite a long time in fact, until 1804, when John Dalton took the idea of the atomos and developed it into tiny invisible spheres called atoms. And the idea about elements was becoming more and more evident at this time, and he took that idea and said that each atom must be of a certain material, must be made from a different type of element. 100 years later. So, Dalton's come up with the idea of the atom, and that sticks around for quite a while. In the interim time, Mendeleev has constructed the periodic table and new elements have been found. 100 years later, J.J. Thomson discovers the electron. The atom is known to be a neutral particle. It has no electrical charge. J.J. Thomson discovers the negative electron and has to try and figure out where they are. He knows they're part of the atom, so what he does is he constructs a model for the atom, a way of explaining the atom, where you've got your neutral ball of charge, but that is made up of a large chunk of positive, which I've represented with red on this rotating sphere, and inside that are dotted the negative electrons, which are represented with the little blue spheres inside the larger model. Its overall charge is neutral because there's a positive bulk to the atom, and then there's the negative charges of the electrons, and the two cancel each other out. J.J. Thomson had a student by the name of Ernest Rutherford. Ernest studied under J.J. Thomson within Cambridge University, and then ultimately ended up taking over the research facilities that were run by J.J. Thomson. Whilst he was doing this, he also discovered a lot of things about nuclear radiation. It's from Ernest Rutherford that we get the names alpha, beta particles, and we'll be talking more about those in a later video. But what he did was he had a group of students who he used to carry out experiments to investigate the structure of the atom. He was basically trying to prove Thomson right. However, the evidence doesn't fit the plum pudding model. It didn't work. It didn't show the kind of results that would say that the plum pudding model was correct, which led to a big question mark. It led us to think, what is the model then? He had to do some serious thinking based on the evidence he had available to him in order to develop a new model. Now, this is actually a key thing within science and within the GCSE process that you need to be able to understand. You need to be able to appreciate the science of the scientific method. This all basically starts with the idea of a scientist will have either some research done or an observation of a phenomenon, and in this case we're using the idea of the atom. J.J. Thomson discovers the electron, and as a result of that he has to come up with a new hypothesis, a new idea or model for explaining it. Now, in order for the scientific community to accept this new hypothesis or new model, an experiment needs to be done. The experiment will collect data. From that data you need to perform an analysis or conclusion and then report on that. If the data matches the hypothesis and the conclusion and the results all tally, then that theory can be accepted and will probably be worked on to develop further. If, however, the results and the analysis and conclusion of those results show the hypothesis to be wrong, you've got to go back to the start of the process, come up with a new idea, a new hypothesis in order to explain whatever the phenomenon is. And this is the situation that Rutherford found himself in. He had evidence to say that J.J. Thomson's model was not right. Now you need to be able to describe that evidence and how it was obtained. It was obtained using the alpha scattering experiment. In the experiment, an alpha radiation source is fired at a thin piece of gold foil. Now, gold was used because it could be made incredibly thin, only a few hundred atoms thick. This experiment was done inside a vacuum, which stopped the alpha particles from interacting with anything other than the gold foil. You'll be looking at the properties of alpha particles in a bit more detail in a later video. Around that alpha source and the gold foil, a detector was placed. Now, in varying different versions of this, you either have a movable detector or you have a big detector screen, a little bit like the blue circle that I've drawn on this diagram. And that detector was basically going to be used to track where the alpha particles went after they'd interacted with the gold foil. The results from the alpha scattering experiment looked a little bit like this. You have your alpha source firing those particles at the gold foil. Most of the particles went straight through, or were deflected by small amounts. Now, that was fine. The plum-pudding model pretty much anticipated that, because the atom itself was neutral, and because there was no real substantial mass of positive charge within the atom, it was all distributed throughout the whole thing, then it could explain small deflections, but it couldn't, and the particles passing straight through could be pretty much explained as there being gaps between the atoms. What it couldn't explain, and the issue that exists, is that very rarely, and we're talking like 1 in 50 odd thousand particles, was deflected back towards the source, back the way they came. And the plum-pudding model cannot cope with that. There was no way that through any kind of interpretation of this big ball of positive charge with the negative electrons dotted through it, you could explain why an alpha particle, which was known to be a positive particle, would bounce back the way it came. So Rutherford took his experiment's results and drew a new conclusion from it, and as part of that conclusion developed a new model. So he came up with a new hypothesis based on the evidence and the observations that he had in front of him. Now, most of them going straight through or being deflected very slightly could be explained by the atom being mostly empty space. So these alpha particles weren't going anywhere near to anything that was capable of making them change direction, or if they were, it was only making them change direction a little bit. The rare particle being deflected back, that was the major stumbling block for the plum-pudding model, could be explained if the mass of the atom was at its center, which Rutherford coined the phrase nucleus for at this point, drawing its parallels from biology and the cell. And it had to be a positive bundle of mass because the alpha particle was known to be a positive particle. In order for it to deflect back and repel, like charges repelling, the alpha particle had to have the same charge as this new nucleus that Rutherford had proposed as an idea. So as I've mentioned, Rutherford developed this new model. He proposed the nuclear model, which had the positive nucleus, which I represented with the red dot, surrounded by electrons in a cloud to make it almost like the ball shape as described in this image below. Niels Bohr developed the model further. He was aware of the fact that electrons could only exist in certain energy levels, and from that came up with the idea that they were orbiting in energy levels, or what we call shells if you want to use the chemistry parlance on it, around that positive ball of nucleus in the middle. The proton got discovered a little bit later on in the process. Again, this was through the similar kind of research that they were doing. Effectively, it came about because they realized that the hydrogen is one of the lightest possible elements that existed. If you ionize it and remove the electron from it, then that ball of positive charge that you have left must be the thing that is the positive charge within all the atoms. And from that, it got coined the name proton. James Chadwick discovers the neutron in around 1932 and uses it to explain why the atomic numbers, the proton numbers, and the mass numbers of elements are different. As you go up through the periodic table, it starts off with them being fairly similar or pretty much the same, but then the heavier elements invariably have more neutrons than protons. And this was one of the issues that existed 100 years earlier when Mendeleev was working through the periodic table, is that the masses didn't go up in a linear fashion. Whereas if you look at the periodic table in terms of the atomic number, it does. So, where are we now? With the discovery of the neutron, and the atomic model now looks pretty much like this, where you've got protons and neutrons in that central area, the nucleus, and that nucleus is actually about 1,000 times smaller than the atom itself. So this diagram is not to scale. This is a representation of a carbon atom with 6 protons and 6 neutrons in the nucleus, and then 2 electron shells. There would be 2 electrons in that first shell or energy level, and then 4 in that second energy level. Right. The size of this thing, atoms have been determined to be around 1 times 10 to the minus 10 meters. So that's 0.1 nanometers, and that is much smaller than can be perceived with visible light. You'd have to use something like an electron microscope to view these things, and that's where some of the stuff that you do in biology regarding magnification comes into play, because you discuss the ideas of using an electron microscope to view these things that are not visible using light. In summary, we went from Atomos with Democritus to the atom with John Dalton to the Plumpity model after the discovery of the electron by J.J. Thomson, and then from that to the nuclear model thanks to Rutherford's experiment, Niels Bohr and James Chadwick. The scattering experiment that was used by Rutherford to develop the nuclear model aimed alpha particles at gold foil. If the Plumpity model had been right, the alpha particles would have gone straight through or been deflected very little, but that didn't happen. Some were bounced back towards the source. Scientific method tells us that they needed to change the model. So Rutherford constructed the model with the mass being in the positive nucleus and the electrons orbiting in a cloud. Niels Bohr developed that model to have the electrons in energy levels, or what we now sometimes refer to as shells, and then the proton was discovered as being a particle which must have been the positive charge inside the nucleus. And then Chadwick discovers the neutrons, and the combination of those last few things leads us to the modern understanding of the atom, which you've been taught about.